we've seen then how a string of length L could support a standing wave of this nature, okay, with one peak, one antinode. We've seen that it can support a wave with two antinodes. And here we have a wave with 1, 2, 3 antinodes. We can also represent a wave in a string fixed at both ends with 3 antinodes, or any number of antinodes if we make this picture extensive enough, but looking at these 3 we get the idea. And we can easily set up the sequence of relationships between wavelength and string length, possible wavelengths and string lengths. We call this the longest wavelength, the fundamental wavelength, and the others are called overtones. Now we can also model sound waves. Here's a hollow tube. Okay, we can see it's hollow. Okay, if I slap my hand on the end of this thing, we hear a certain vibration. We hear a certain frequency of vibration or certain pitch of vibration. And what's happening there is I'm sending out all kinds of pressure waves here. Sound is a pressure wave, and you can read about the nature of it, but when I do this, I send alternating high and low pressure signals or regions of high and low pressure down this tube. They reflect at this end and come back and reinforce, and then they reflect again. Okay, that goes down here, reflects, comes back here, reflects again, reflects again. Now, if they have just the right wavelength, they can reflect in such a way as to set up something that can be represented, although this isn't a good picture of the way a longitudinal wave behaves, could be represented by this sort of picture. And the node-antinode sequence acts in a very similar way, and we'll get into that. Okay, what we have here then, at this end of the tube, after I leave my hand, after I move my hand away, this end of the tube, the air is free to oscillate. So there's an antinode here. And the same over here. This end is also open, as you've seen, so that the air here is free to oscillate. So we have antinodes at both ends of this tube. Now, if you have antinodes at both ends, we can see that. Right here is an antinode, and here's an antinode. Or even here's an antinode and here's an opposite antinode, so that we could let this be the length of our tube. We have an antinode at this end and an antinode at this end. Okay, a point of that reaches maximum displacement as we move through time at this end and again at this end. So if this is L, it's a tube length L. Implies what? It implies, well, how much of a wavelength do we have between this end and this end? Half of a wavelength. So that lambda, again, equals 2L. The wave is different in that you have antinodes at the ends rather than nodes that you would have at the ends of a fixed string, but the analysis of the wavelengths, of the possible wavelengths, is practically identical, completely analogous and practically identical. So for the string, we see that we go from a node at one end to a node at the other. Now that's for a string that's fixed at both ends. That's what dictates that you have nodes at both ends. We have a node at each end. Node, node. And of course, between any two nodes, there's an antinode. So it goes node, antinode, node. This one goes node, then there's an antinode and a node and an antinode. Okay? And this one you can see it goes node, antinode, node, antinode, node, antinode, node. Here on the tube, it goes antinode at end, antinode at this end, node in the middle. If we went from, let's say, this antinode to this antinode, then what would we have? We would have if this is the length L, we have antinode here, and then we're going to have a node and an antinode and a node and an antinode and a node, and then our final antinode. And we can see that very clearly in the way the graph develops. Now we have another type of tube, sealed at one end, open at the other. I can do the same thing with this one. I get certain frequencies that tend to reinforce one another, reinforce themselves. I guess that's more accurate. And let's see, what color chalk am I going to use here? Pause the video for chalk. Okay, green chalk. At the closed end, the air can't vibrate. It's up against the end. At the open end, of course, it can. So what you have in this case is an antinode on one end and a node on the other. Where can we find that sort of behavior? Well, here's an antinode, here's a node. We could do that just between here and here. If this is the length of the tube, we see that one-fourth lambda equals L, so that lambda is 4 times the length of the tube. Now, how else could we get an antinode at one end and a node at the other? Well, we could go from this antinode to this node, let's say. So we could go from here to here, and let this represent the length of our tube. Okay? Then what do we have? We have 1, 2, 3/4 wavelengths. 1, 2, 3. So we have 3/4 of the wavelength equals L, so that the wavelength is 4/3 L. I'm going to suggest that you should take time right now and write down, let's say, the first 5 possible wavelengths for each situation. First 5 wavelengths for a string fixed at both ends, and you should make yourself a sketch of this and see where the string would span on this picture, and see if you can then find the pattern of wavelengths. What would the nth wavelength be? The ultimate question. So what is the nth wavelength for this? What's the first, second, third, fourth, fifth? What's the pattern? So how could you use that if I give you any number well, if I give you the number of any harmonic, okay? If I went to get the 12th shortest wave or longest wavelength, what would it be? How could you do that without writing out the whole sequence? And the same for the tube. Of course, the sequence is going to be identical for a tube that's open at both ends, but for a tube that's closed at one end and open at the other, you get sort of a different sequence of possible wavelengths in terms of the length of the tube itself. And I've added a little bit here. Tube closed at one end implies, if this represents the tube, you have an antinode at one end, a node at the other. The node being at the closed end, the antinode at the open end. And you look at the antinode-node sequence. If we model the length of the tube as just 1/4 wavelength, well, then the wavelength is going to be 4L. If we go from an antinode and skip a node in an antinode to get to the end node, then we have 3/4 of a wavelength. Wavelength is 4/3 L, etc. Again, you should be sure you completely understand this scheme and how it's derived from this picture.